So I'm going to very quickly at a top level go through what spectroscopy actually is, because I appreciate some people on this call may have spent lots of time doing spectroscopy, may be really experts in it, and some people may have never come across it before. So I'm just going to run through it very briefly at a top level, just to make sure we're all on the same page. Spectroscopy starts with a bulb. This is my badly drawn light bulb that generates a light source. So this is our light source. It generates light of the wavelength we need for spectroscopy. And we can use any type of wavelength, and I go into that on the next slide. But we have to generate our light in some way. This light is then shone through the sample of interest. So we have to get the light from the bulb to the sample somehow. The sample itself either absorbs or emits light depending on the type of spectroscopy we're looking at, but effectively it changes the light in some way. So then our new beam of light, it's a different color to start with, so it's changed light, has to then go into the rest of the spectrometer, and then we have some kind of optics that manages this light and breaks it up into such a way that we can put it onto a detector and come to a conclusion as to what it is. And you see spectroscopy every single day. If you've ever walked into a room with a light bulb, that light bulb gives out white light. It gives a range of different lights, and they all average out to be white light. If nothing ever changed the light, then everything in the room would look pure white because they would just be reflecting that light back at us. But they don't. Everything in the room looks the color of whatever it is. I'm currently sitting in my study. I can see some black furniture, I can see some green furniture, I can see some lovely magnolia walls. They're all reflecting the light at different colors. And that is, in its simplest form, spectroscopy. What we do as spectroscopists is take that data and turn it into a quantitative measurement. We see how much of that light comes out green, how much of that light comes out red. And that's what spectroscopy is. As I said, there are loads of different types of spectroscopy. This is the electromagnetic spectrum, and we can use pretty much all of it. So at one end, we have the high energy, short wavelength lights, and that's down here with the gamma rays and X-rays. And we tend to use that for looking at crystal structures. We then move into UV, and we tend to lump that together with visible light, and we call it UV-Vis. And that looks at electronic transitions within molecules, which is higher energy than infrared. And infrared looks at vibration within molecules. So that is the chemical bonds within a molecule vibrating. So if we think of something like a water molecule, we have our oxygen in the middle, and we have two hydrogens, one on either side, and that oxygen to hydrogen bond can vibrate. And that's what we're seeing. Molecules are basically made up of springs. They're atoms that are all connected by springs, and all of those springs vibrate at different frequencies and wavelengths, and that's what infrared light looks at. Then we have microwaves. Microwaves look at rotations of molecules, because molecules don't just sit there. They don't sit doing nothing. They're constantly moving, and the rotation frequency and energy corresponds with microwave. And then radio waves are what we use for nuclear magnetic resonance, or NMR, or MRI. Anyone that's ever had an MRI scan has had radio waves shone onto them in a giant magnet, and that is basically all that is. So the whole spectrum we can use for spectroscopy. For PAT, we tend to focus on UV-Vis, near-infrared, and infrared. The near-infrared, by the way, is this bit, sorry, it's just here, this bit just here, between the red that we can see and the infrared. That's what the near means. It means close to the bit that we can see. So we have near-infrared here, we have mid-infrared in the middle, and far infrared, which is the stuff that's far away. It's not a complicated naming system. So for online spectroscopy, we have UV visible and fluorescence, and these both use the ultraviolet frequencies and a little bit of the visible, and that's electronic. The good for this is their simple interpretation of the results, and they can be very sensitive, but they only work for a few niche applications. You need a molecule that undergoes an electronic transition, and that means it has to have double bonds and triple bonds inside it. Single bond saturated molecules don't tend to undergo those transitions. So for example, the vast majority of free fatty acids, certainly the saturated free fatty acids, would be very difficult to analyze with UV-Vis. The carbonyl peak in those might do something, but it's not going to be a trivial measurement to make. And then we have this grouping of vibrational measurements down here. And we have Raman spectroscopy, which is a very special type of spectroscopy. I'm not going to go into too much detail on it. It's like mid-infrared in the type of information it gives you, but there is something called a selection rule for it, which is dwelling far too close to quantum physics for a lunchtime webinar, that makes it very difficult to use for some applications. And it can fluoresce, and fluorescence with Raman can make it very difficult to use. And then we have near infrared, classical mid-infrared, and the static optics infrared of what I'm talking about today. They're both the mid-infrared and static optics infrared are both very information rich, but the moving parts in mid-infrared make them unsuitable for industrial applications. So they have a set of mirrors that have to move along a track, and that track must be extremely well determined and well controlled. If there's any vibration present, that track becomes much harder to understand and it throws off the instrument. Getting around that with things like fiber optics, the fibers are far too fragile and they can literally get broken, or they can be bent out of place, or it makes them very unsuitable for manufacturing environments. I'm going to talk about near infrared in more detail in a second. So how do we actually use spectroscopy? We have to build a calibration. So it isn't inherently quantitative. We do have to build that calibration first. So the first thing we do is we acquire calibration spectra. We can either do that by making a sample set up in the laboratory, or we can piggyback on normal production runs and campaigns, especially when there is a natural variation in the process. And I've got a couple of slides, one for each in a minute. And then we use a reference set of concentrations, and we use the two together to build a calibration model. Now you can do this using the classical way of peak heights, where we use something called Beer's law, or you can use chemometrics, which we use almost exclusively. It is orders of magnitude more powerful. It looks at the entire spectrum in one go and pulls out the individual subspectra of different chemicals. It's a bit like trying to read a barcode by eye. A human might be able to recognize a barcode if they have a reference for it, but trying to read multiple barcodes overlapping on top of each other, impossible. But a computer can pull that out, and that's what chemometrics does for us. And then once that calibration model's been built, we take offline samples randomly to validate it, because that's good science. You don't want to install something that might not work. And we do constant statistical checks on that to check that the model is working as it should do. And I'm happy to go into more detail on those later on, but they're not part of the main flow of this presentation. So near infrared. Some of you may be sat there thinking, yeah, we heard all about infrared before. It was going to fix everything, and it didn't. I tried a near infrared and it was awful. It was expensive. It took me ages to calibrate. It didn't work. I must stress this: near infrared and mid infrared, or FTIR as it's sometimes called, are different. They are very, very different. Unfortunately, the infrared part of their name is the same, but they are very different. They're both based on vibrational information, but the quality of the information is completely different. So this is as close to quantum physics as I'm going to get, I promise. When we have a UV-Vis spectroscopy, so this is the electronic, or mid-infrared, also called FTIR, we have a fundamental spectroscopic interaction. So we start in this what's called the ground state. And in electronic, we jump up a rung of this electronic ladder. And you'll notice we're still in the vibrational ground state up here, but we just jumped up an electronic state. And for mid-infrared, we start in the vibrational ground state and jump up to the vibrational excited state. In both these cases, we've only gone up one rung on that ladder, which means it's very easy to understand what has happened and what's caused that to happen. For near-infrared, we jump up multiple rungs on that ladder. And it's very difficult to work out how many rungs you've jumped up, what this actually correlates to, and what you're looking at. What that means is that near infrared, so this is called combination and overtones rather than fundamental transitions, they are much harder to identify. And near infrared struggles to differentiate between similar molecules. For example, free fatty acids, cis-trans isomers, mono, di, and triglycerides. Identifying the difference of those with near infrared is extremely difficult and requires a lot of calibration standards. And that is probably why, if any of you did try it and it didn't work, that's why it didn't work. It is a really hard technique. Now, for things like solids, And you just want to look at a classic example is water in meat, or water in grain, or probably water in seeds. NIR does a reasonable job of that. But trying to get down to the more detailed in situ processing in liquids, it's much, much harder. I like to use this as an example of the type of different information we get. With near infrared, you effectively get a silhouette. It's that kind of granularity of information. And here we have a picture. Is it a vase or a vase, or is it two faces? So are we looking at the white or are we looking at the black? With mid-infrared, we get very, very clear that it's a vase. That's what we're looking at. We get that depth, we get much more information. We can really understand what's going on. One